Welcome back, everyone. In this lecture, we're going to go through the solutions for your principal component analysis project exercise. Let's head to the notebook. Okay, here we are at the project notebook. Let's scroll down till we get to our first task, which was simply to run the cells to import the libraries and relevant data set. So we have NumPy, Pandas, Matplotlib, and Seaborn, and this is going to read in the 𝑑𝒓𝒐𝒋𝒆𝒄𝒕 file. And then we have our digits data frame. So it has the pixels, and remember this is 65 columns. So if we scroll all the way to the right here, we have this number label column. So continuing on, we want to create a new data frame just called pixels that consists only of the pixel feature values by dropping that number label column. This is pretty simple to do. We're just going to say pixels, or really whatever you want to call this, and then we're going to say digits or df, and then we're going to say drop the number underscore label column, and it's a column, so we have to say access is equal to 1. And so if you call pixels now, let's zoom out just so we can see a little better here. So if we call pixels, you should pretty much get the exact same thing as before, but it's 64 columns, meaning it's only the pixel feature data. Okay, next we want to display an image. So with a quick Google search, you should be able to find out that it's actually pretty simple to do, where we're just going to need to convert this to a NumPy array and then use plt_imshow. So we first want to grab a single image row representation, get the first row of pixels in the data frame. So we simply say single image is equal to pixels, and the way we can grab a first row is ILOC. So that's integer base location, and grab 0. And this will give me a pandas series, single image. There we go. So we have this pandas series, 64 values here for the actual pixels. Then we're going to convert this single row series into a NumPy array. You can pass this into NP array, or you can actually just say single image and then call to underscore NumPy. And that will actually convert it to a NumPy array as a method. Or you can say NP array and cast it into an array. Either way is okay. And then recall we want to reshape this NumPy array into an 8x8 array. So right now, if we were to check the shape of this, it is currently just 64 on a single row. What we need to do is convert this to be 8x8 in shape. So what we can do here is say single image to NumPy, call reshape 8x8, and you could do this in multiple lines if you want to keep reassigning this, but if you do it in one line, it's actually the exact same thing. So here we have now our single image to NumPy reshaped as 8x8, and I'm just going to call this, for example, number is equal to single image to NumPy array reshape. So when I call number now, it has that 8x8 array. And now we can use Matplotlib or Seaborn to display the array as an image representation. Lots of different ways we can do this. One way is to say plt_imshow, and then we just pass in that number, and there you have it. NumPy will automatically display this. We can also change the color mapping here. So if you wanted it in grayscale, you could pass in grayscale. Keep in mind, they're just values, so there's not actually any sort of color information here. If you learn more about images, you'll realize for color, you would need a 3-dimensional array with red, green, and blue values. Right now, it's just a bunch of single pixel values that go from 0 to some number, so that just gets attached to the color mapping itself. So color mapping here is kind of meaningless because in reality, it's just a grayscale image because it doesn't have multiple color channels. Instead of using plt_imshow, which you could have also done, is just call SNS heat map and then pass in number there. And you would have gotten a heat map, and if you really wanted to, you could also say annotation is equal to true to see the annotated values as well. All right, so we have the idea here. Clearly, it looks like a 0, so let's move on to the PCA portion of the exercise, which was starting off with scaling the data. This should be pretty simple. We're going to say from scikit-learn preprocessing, import standard scalar, create an instance of standard scalar, and then we're going to say our scaled pixels is equal to scalar, and I'm going to fit transform the pixels data frame we created last time. So recall pixels was this 64 feature set, and then scaled pixels is going to be the exact same thing, but it's a scaled NumPy array. So now we have this, which is ready to go for PCA. All right, so let's move on to PCA now that we have our scaled pixels. We say from scikit-learn dot decomposition import PCA. Whoops, decomposition, need to spell that right. Sometimes it's just easier to use tab autocomplete there. There we go. And now let's create our instance of the PCA model. Pretty much the only thing we need to pass in here is the number of components. And we specified we want to go down to 2 components for easy visualization. And then we'll say PCA pixels is equal to PCA model. And I'm going to fit transform the scaled pixel data set. Okay, so now we have the pixel data that has been scaled or normalized. So now it's centered around mean is equal to 0. And then from that, we projected that down to the 2 eigenvectors, or those 2 principal components. Now we want to ask ourselves how much variance is actually explained by those 2 principal components. And recall, you grabbed this off the fitted model. So we can say PCA model, and then there's explained variance ratio. Explained variance is actually still in units, so it's not actually still super helpful. It's in the units of the scaled original data, so it's really hard to interpret. Instead, you should be looking for the explained variance ratio, which is in terms of percentage, much more understandable. So we can see PCA model explained variance ratio. You can see the first component explains about 12%, second component about 9%. If you wanted the total explained by 2 components, just ask for the sum here, and you can see it's about 21.5%. Next, we want to create a scatter plot of the digits in the 2-dimensional PCA set. So how do we actually do this? This one's slightly tricky, but lots of different ways you can actually create this scatter plot. I like using Seaborn's scatter plot capabilities. So we have to think of what are we actually trying to plot here. Recall, we right now have the PCA pixel data. So if we look at PCA pixels, it's a NumPy array that has the first column for the first principal component and the second column for the second principal component. And what I can do is I can just grab each column by saying colon, grab all the rows, and then 0 would be for the first column. So notice I have 1.91, 0.58, 1.3. If I just pass this, now I have that first column of data. If I wanted the second column of data, that's at index 1, and now I have this. So what we have here is a way of grabbing the actual columns that we're interested in. So I'm going to say create a scatter plot of the first column, that first principal component, against the second principal component right here. So we're just saying first column against the second column. And if you just run this, you'll get kind of this scatter plot. Keep in mind you may get a warning here that it's going to require you to actually say data in the future. But for right now, we should be okay with this. The other way to do this is with PLT scatter. And it'll produce kind of the same thing, but it won't be as nice as Seaborn, so just keep that in mind. Okay, so you can be using PLT scatter or SNS scatter plot. It just depends on what library versions you're doing and how you actually want to pass in the parameters. But they're pretty much the same thing. In fact, SNS scatter plot is just calling Matplotlib's scatter in the background. So I call SNS scatter, and this is pretty much ready to go. It's just asking for how do I want to color this. So for that, I can pass in the hue parameter, and I can call it based off the labels. And the labels, if we come back to our original data frame, which was digits, recall our digits data frame has that 65th column, which is the actual number label. So I can say, give me that number label right here. So I have these number labels, and if I just want the values, I now have a NumPy array of those. So I can say digits hue is equal to these values right there. Run that, and now we're starting to get somewhere. From here on out, it's just a idea of making this look a little nicer. So what we should probably do is right now it's on a continuous color scale or C mapping. What we want to do is change that. So we could say here is the palette. Let's start putting this on 2 lines here. Palette is equal to some categorical mapping. So you could check the color mapping documentation on Matplotlib. Set 1 is what I like to use for categorical data, because we can think of each number here as a separate category. And now we start to create that same scatter plot we saw in the solutions. And from this, we can just make it a little nicer. So I can say PLT figure, fig size is equal to 10 by 6, make the DPI a little larger, like 150. And then we can move that legend as well. I can say plt.legend and move that to a location a little further outside, so like 1.05, and put it somewhere towards the bottom. And there we have it. So just as I explained previously, we want to look for the clusters or the kind of numbers that are further separated from the ones that are right on top of each other. So clearly, the numbers that are most differentiated are probably like number 4, number 6, and the number 2, maybe even number 7 as well. These ones that are right on top of each other, even when you reduce down to principal components, it's hard to tell those numbers apart because in this principal component space, they're right on top of each other. So the numbers that are most unique or differentiated, essentially easy for a machine learning algorithm to recognize in the future, are the ones that are going to be furthest apart from all the other numbers. So that's something like number 4, number 6, and then maybe number 2 as well, and a little bit of number 7. The troublesome ones are the ones that are kind of all over the place. So 0, you can kind of see it's kind of hard. Number 5, extremely hard. It's right on top of almost every other number. And then we also have the number 1, kind of tricky as well. Okay, so this was using SNS scatter plot as a reminder. You could also use PLT scatter. You're just going to have to change some of the parameters here. So hue, I believe it's going to be C, and then palette would be CMap. Run that, and you would essentially get the same result here, except then you would have to add in legends, etc. But same idea. You just call PLT scatter. Just the parameters you're going to end up passing in are going to be slightly different. You have to also assign that legend, as we've previously discussed in the Matplotlib lectures. All right, now let's go ahead and move on to the fun part. We already talked about which numbers are the most distinct. It's time for the bonus challenge. The bonus challenge was to try to create an interactive 3D plot of the result of PCA. Now we've mentioned that we're really limited as humans in our ability to see beyond 3 dimensions visually, but so far we've only seen 2 dimensions, so how can we actually interact with a 3-dimensional plot? First, let's create that decomposition. So in fact, we can just say new PCA model is equal to PCA and components, but this time I'm going to set it equal to 3, and I'm going to say PCA model, whoops, here we go, PCA model, and I'm going to have it be fit transform on those scaled pixel datas. And then I'm going to say PCA pixels. And if you take a look at Stack Overflow, you'll realize that you can say from MPL toolkits, and we've talked about this before in another previous bonus challenge, you can call mplot 3D, and then this allows you to create a 3D scatter plot. And the way that works is you create a set of axes, and you say plt.axes projection is equal to the string 3D, and then you call ax scatter 3D, and then we're going to pass in PCA pixels. And now we're going to pass in PCA pixels. Whoops, don't want this as a list. And we're going to pass in the first column, the second column, and the third column. Essentially the same thing as before, except now there's 3 columns to consider. Okay, so we have the first column, second column, and third column. So if you just run that, you should see this 3D projection, but we need, oh, this should be a capital D. There we go. So we see this 3D projection, but we haven't actually made it interactive, and we haven't labeled the actual numbers. So for this, scatter 3D, if you take a look at the documentation online, you have C here, which is what you're actually going to color by. So C is the color sequence. So for that, we're going to say C is equal to, and we can just grab that original digits data frame and pass in the number label. Okay, let me zoom out one more here so we can see the whole thing. So we right now have PLT axes, tell it it's the projection 3D. That created the actual axes 3D grid. Then we're going to do a 3D scatter plot on it, column 1, column 2, column 3, and then we're going to color it by those number label of the digits. Put a semicolon here so you don't see this kind of text printout. Run that, and we get this nice plot. And if you want to make it even larger, what you can do here is use the same thing as before, say PLT figure, and just make a larger fig size. So a fig size could be something like 8 by 8, and if you want, you can use a higher DPI. Come back up here, and we see this really nice looking plot, and if you want, you can keep doing stuff like adding a legend to it. So you can say PLT legend, and then you'd have to eventually define the legend. So you would get the actual numbers themselves. But right now, what I want to do is focus on how do we actually make this interactive. So what's nice about notebooks themselves is they have this special notebook tool. So what you're going to say is %, and you're going to say here Matplotlib space notebook. And what this is going to do is it's going to make all these images interactive. So if you run this, and now I'm going to have to really zoom out, you will now get an interactive version of the notebook that you can then, or the image that you can then rotate. And notice here, I'm able to rotate this. It's a little slow on my computer because I'm also recording the screen at the same time, which causes it to be a little slow, but I am now able to interact with this, and I can also pan using the pan tool, and I can rotate this as well. So this allows you to fully interact and kind of explore the scatter plot. Keep in mind, it is limited in its usage compared to something like Plotly or Bokeh, where it's kind of troublesome to try to zoom in. In fact, I don't think you can even zoom in with Matplotlib Scatter3D, but it is a quick one-liner to make this suddenly interactive. And then when you're done with this, you can click the off button, which right now you can't actually see because I was so zoomed in when I ran this. But keep in mind that when you run Matplotlib Notebook, it's going to affect every single plot in your notebook. So if you start trying to run these scatter plots again, you may get some troublesome results. So if I try running this again, suddenly it's going to look like it's interactive. And you can see this little off button to turn it off and make it back into a static plot. Okay, so definitely check out the documentation more if you're interested in Scatter3D and Matplotlib Notebook. But this is kind of just a quick way to make it interactive so you can kind of rotate and take a closer look at things. All right, hope that was enjoyable to you. Thanks, and I will see you at the next one.